Here, how to take into account that some big organization with bronze beverages with multiple fluids. We take this today 2 hours, tomorrow at the same place from 9. Okay.
9.
From 9 a.m.
Okay.
Yeah, for 9 we do.
Okay, perfect.
2 hours.
Perfect.
2 hours.
Perfect.
So thank you very much. Feel
at home.
Yes. Come on.
Yes, thank you, Thomas. Thank you. Well, it is a pleasure, great pleasure to be back. This is my second time in Seville. The first time was at the ECM a couple of years ago, and it is. I'm really glad to be here. It's a nice group. Thomas is correct. So both groups are working, on similar problems. It's a natural connection. So I really enjoyed my visit. And today I will talk about the type of stuff. So ROM reduced order models, ROM stabilizations, and closures for turbulent flows. Okay, so that's the goal. But so it's the talk is made up of several components, and since we've known each other for a while, please stop me every time you have a question you want to ask. So this is not gonna be about me presenting stuff. I have to say that most of the stuff I will present is not final. It's up for discussion, for improvements. So, and right, I mean, if Thomas says, Fran, but I think we can do better, that's probably true, but let's discuss that and we'll take it from there. Yeah, okay. So, and please let me know, I mean, so you can ask me any questions you want. Once again, by no means, we've been working, in our group, we've been working on this for a while, but if you have better ideas or better ways to do this, just let me know and we can talk about this, right? Okay, at any point in time. Yeah? All right, very good. Okay, so right. So the other thing is that most of you know ROMs very well, and LES, yes, and the larger simulation. So I'm gonna try to connect these two things. So if it is too boring or is too basic, please let me know, and we'll take it from there. Yeah. All right. Very good. Okay. So. Okay, this is, so the talk is very long by my standards. So this is a long list of collaborators, and I would want to start with my academic family, students and postdocs. And some of you recognize, you can see your names here. And different people contributed at different points in time, and I will make this clear when I go through each slide. Okay, but also collaborators. So I have very strong collaborations with with CISA, also in Italy and the US as well. And you can see here Thomas and Samuele. So I don't know if Samuele is connected, but his name is here. And what I want to emphasize is that this is the only group who has, at least for now, has like ... And the more, the better. All right. I don't know if you got my meaning, but that's that. Okay. So lots of people worked on this and different points. And I will talk about that. Okay. Gracias. Okay, so I will start with something generic, and then once again, since you're specialists in this subject, so tell me if it is too slow. But then I will do something maybe a little bit different. So I will divide my talk into 3 parts. So the first 2 parts are about the use of spatial filtering, and I think that this is nice. So and maybe that's a little bit different from what other people are doing. And I'm going to use the board to write stuff, all right? So the first part is about classical numerical modeling, larger simulation. And the second part is about reduced order model. So it's the same idea. So the idea of spatial filters is the same. It's just that its use is different. The first part, larger dissemination. So once again, this is a classical numerical method. So I don't expect too many questions. It's gonna be short.
¿Quieres verlo tú también? No. Claro, te empezó. Bueno. Vale, acaba de
But
empezar.
because this has been
Vale,
around
pues
for a
luego-
while.
Vale, pues
Yeah?
luego te cuento.
Okay,
Bueno, de
come
todas
on.
formas, como estoy con el Teams, si te
And,
funciona el programa, me lo dices. Y lo voy
This
mirando
is,
también.
This is
Sí.
we're good.
Vale. Hasta ahora.
So the second part is a little bit more debatable. So this is about reduced order modeling, the use of spatial filtering in reduced order modeling, and this is that's the part that I will discuss more. So most of the focus is gonna be on this second part. Okay, so this is gonna be a little longer. Right, but then the third part, which I think is it's probably the new part, is that's what we call the stab up. So this is a data-driven approach to spatial filtering, and this is gonna be different. So here, I expect a lot of questions. So no questions maybe or very few questions for the first part, more questions for the second part, and definitely lots of questions for the last part. Let's call it 3, yeah? So this one is the one that it's new and you know, we can argue about that, right? And then I will end up with some conclusions, right? Okay, so that's the idea. So let me start, and I will be brief, right, with the motivation for what we're doing. Okay. All right. So what are we doing? What are the problems that we want to tackle? Right? And I know that every reduced order modeler is showing some pictures that are similar to this. But in our case, so you'll see that there's some requirements that actually make this problem a little bit more difficult, I think. So the ultimate goal, we haven't gotten to that point, but the ultimate goal really is about getting ROMs in commercial software. So what I mean by that is that I would like to have a button when I'm using ANSYS or Abacus or, you know, commercial software. I would like a button that says, okay, if you push this button, then we're gonna use this type of ROMs. So to be automated, right? But and used by engineers on a wide scale. That would be one objective. The second one, and I think that's important, is to deal with real turbulence. And you'll see what I mean by that. But you see, so again, every ROMer is showing some picture like this. But then if you ask, have you ever done this? Well, I cannot say that I've done it either. But this is exactly what we're trying to do. We look at the flow in a wind farm. This is a geophysical flow. And I would like to have commercial code to solve these problems. Yeah. Okay. It has to be real turbulence. I don't want to do this for academic test problems. We use those as well, but just to test our models, but they're not an ultimate goal. And I think that this is important because most of the models, ROMs, work well on academic test problems. And I would say that the vast majority of ROMs fail for this type of flows. I think it's a brutal statement, but I think that that's the truth right now. Okay, and the third requirement, I'm a mathematician. I would like to have some proofs for what we're doing. So there is turbulence, so it's not gonna be clean, mathematically clean, but right, so it's one of the most difficult problems. But I would like to know that we have similar numerical analysis results, like for standard methods, like finite elements and finite differences. When people say these are second order methods or they're stable, I would like to have something similar for what we're doing. So this is the third requirement, okay? All right, so far so good. I think we're good. Yeah, but so the pictures are important, but I think the most important things are the requirements. So that's what we want to. Okay, so I'll go through this. The first part is non-technical. Then it's gonna get a little bit more technical. I'm gonna write more on the board, but okay. So what are we trying to do? The strategy that we use here is to bridge two distinct fields, and we've done this for 2 decades. Well, it's not 2030, but okay. Yes, and they're distinct fields, research fields. So they're books and papers and big shots in each field. One is largely simulation, and the other one is induced order modeling. LES is a classical field. I would say that, so it's been developed for many decades, and I would say that, I mean, the basics, the foundations have already been laid. They're open problems, but overall, well, for one, you have commercial code that does LES, right? If you buy commercial code, you have a button for the Smagorinsky model, right? Right? Similar for RAMs, right? So you do have that. Now, the second field is not as well developed, reduced order modeling. So yeah, that's where things are becoming a little bit fuzzier. And the sales pitch is to combine the two, and I would focus on the principles, like not that much. So I'm not trying to sell you one model. I will not say this is the model, my favorite model. Well, I would say that, but I'm not asking you to use that model. You can discard it, absolutely no problem. But I would like to discuss whether the principles, the ideas, you agree with those or not. Because if you say that's a bad idea, I really want to discuss that with you. All right? Okay. So for this, we're going to take 2 different, directions. One of them is closures, and the other one is stabilizations. I'll talk about those. So right? So the title of the talk is Closures and Stabilizations, and people say, well, aren't they the same? They can be very similar, but they're not exactly the same. Yeah. So we're gonna talk about that. Okay. All right. So a little bit of So what is the idea? This is our book from 21 years ago. It's the Mathematics of LES. I wanted to include Thomas's book, but yes. So then, right? So I'm just, I will see some more books. So they're books not only on LES, I'll talk about that, but they're books on the mathematics of LES. Thomas wrote one, we wrote one, Volker wrote one. So this gives you an idea about how well established this field is. You write about proving things about the models that are already in use. Now, how about reduced order modeling? And this is a physics of fluids paper from 5 years ago, actually, with a survey of closure models. And if you want to read more, I'm not going to present all the models today. I'm going to present the models that we developed in our group, discuss those ideas. And if you want to read more, you can ask me, and I can point you to surveys. And to my knowledge, there's no book, but definitely to surveys and more background. Okay, very good. So this is looking good. Now, this is another paper, a more recent paper that I wrote with Annalisa Acquaini, Omer San, and Alessandro Veneziani. And this is exactly about what I'm trying to talk about today, how to use spatial filtering. Once again, that's the type of approach that we're using, but you can develop closures and stabilizations without explicit filters. And I will not talk about that. Okay, it's a good question. How do they compare, right? But I will not talk about that. Okay. Well, I will tell you why we like this. So I will tell you why we use this approach, but I'm not criticizing or saying, right, you shouldn't use other approaches, right? I mean, each approach has its pluses or minuses. It would be nice to compare them. We compare some of them, but I'm not aware of a comprehensive investigation, comparison of different types of models. That I don't know. Okay, very good. So this is background. Right, and in terms of like background, so we even organized the conference That was in 2024, that's Atlanta. And we're thinking about organizing another one, a follow-up. And what I think is nice about it is look at the name of the conference. So it is ROMs plus machine learning. I really think that data should be part of this. This is a very good direction. This is right. But the focus, so the target is was LES and related topics. I would say for fluids, turbulent flows, I think this is still an open problem. Nobody, to my knowledge, nobody has the perfect solution for that. Okay. Okay. Right. So the final page for the introductory part is how will commercial software for ROMs for fluids look in 2030? And our answer is LES ROMs of some sort. Okay. Right. So a combination of these two, I think it will be used in commercial software for turbulence. 2030, you know, this I started to have this slide a couple of years ago, to use this slide a couple of years ago, and maybe it becomes a little bit optimistic. but the rest I still believe in, right? So commercial software for turbulent flows, I think it will involve some sort of LES ROMs. Okay. This is that. Now, so any questions so far? This was a motivation. No, should be boring, should be easy. Very good. So LES. So you know, so we have some specialists here. People wrote books. Thomas wrote a book, and but I want to explain what I mean by that. And to me, the easiest explanation is schematic. Is a schematic of this form, in which this is a classical schematic. So you have a signal. You can think of this as a one-dimensional version of your velocity field. That's U. And then you want to represent it on a coarse mesh. You see, that's important. So this is, I want you to remember. So the mesh that we're using is coarse, and then we have a function, a graph that we want to approximate on the coarse mesh. Okay, now you can say, so why are you interested in that? And the answer is very simple, is when you deal with turbulence, the vast majority of numerical simulations are under-resolved. You cannot afford, if you're an engineer or geoscientist, especially a geoscientist, you cannot afford the computational power to fully resolve turbulence. That's out of the question with numerical methods. Okay? So this is a practical problem. It's not like I'm not a mathematician who says, oh, let me imagine a possible scenario. No. This is a practical problem. This is an under-resolved simulation. So the question is, how do you resolve it? And the answer is that you cannot, right? You cannot obtain all the structure in the flow. But what you can do is very simple, right? So this is the mesh. That's an exaggeration, right? So you have something like this. Well, what do you do? What you can do, this is your U, you do something like that. So in blue, we have U bar. I'm not using the same colors, but that's okay. And then in white, you have your U. We cannot approximate U here on this mesh, but we can definitely approximate U bar, right? So U bar would be something like that looks, I mean, hopefully looks something like this. Well, I mean, okay, maybe this is not the best one, but okay, yeah. So it does. Okay, so let's put another point here, and let's call this one H. Fine. All right. It's still under resolved. It is still under resolved, and you can still you can't resolve it with these few mesh points, right? I want you to remember this picture because this is the core of what we're gonna do. Okay. Now, so what is LES about? Very quickly, because I think you know this very quickly. The idea is very simple. So you have equations for U. These are the Navier-Stokes equations. They give you the velocity and the pressure. And then what you do is you filter them. So you get the filter Navier-Stokes equations. They give you the U bar. So you go from U to U bar, and the equations for U bar are the filtered equations for U. All right. Now, so this looks great. I mean, this looks great. However, as we discussed this morning, we've been discussing for a while, we still have no final answer here. These filtered equations are challenging. The filtered equations are challenging because they look very close, they're very close to the usual Navier-Stokes. Instead of U, though, you replace U with U bar. But in addition to that, they have a term, an extra term, that accounts for the nonlinear interactions. Not only, but. Yeah? So we have to be a little bit careful. It's not the same set of equations, usually it's more complicated. And then you have to supplement the standard Navier-Stokes equations with some extra terms. Okay, but this is the idea, and we're gonna get back to this. Okay, well, you've seen this, but I hope for maybe those online or here that have not seen LES ever, this is the cartoon of LES. Okay, now the books, still Tomas's book is not there, but okay, so what I want to say is this: there are hundreds, if not thousands, of LES models, many models. And if you ask me which one, what the best model is, if you ask anyone, it's gonna be very hard to answer this. But there are hundreds, and in use, so practical, in practice, people use this in commercial software. This is Piersago's book. And then one thing that I want to emphasize, because I always get this, very similar questions, is it's true that this book is for incompressible flows. But look at this one. This is largely a simulation for compressible flows. So it doesn't mean we're not restricted to incompressible flows. LES, similar, not the same. You have to account for compressibility, okay? Filtering changes, but you have the same principles used for compressible flows. Huh? There's some confusion. I always get questions like, oh, but the tricks that you're using cannot be applied for compressible flows. And my point is that, well, they've already been applied for compressible flows. Yes. So don't let people, criticize your work because it's compressible, it's not compressible. Okay, very good. So now probably, so this is a slide that I would like to talk about a little bit. Any questions? Generic questions? No? Okay, so this is something that how should I put it? So I will use this slide when I talk about reduced order modeling, LES type of model, closures and stabilizations. And this is standard for LES, but it is not standard for reduced order modeling. So in LES, when people test one of the 100 or 1,000 models, usually one of the classical test problems is the turbulent channel flow. So this is, how many of you have done turbulent channel flow? You've seen that. Okay, very good. So you have two parallel plates. That's the idea. So these are two walls, let's say. And then flow comes from the left, gets out to the right. Okay. It is turbulent. It has to be fully developed turbulence. As I said in my previous slide, I do not want to take a very fine mesh and resolve it. I can do that, and I want to emphasize this. So there are fully resolved turbulent channel flows, and this is a paper that has. Have you heard of this? You must have seen this. This is Moser, Kim, and Mansour, 1999. It has thousands of citations, thousands, 10,000, 20,000. I don't know. And there's a newer version by Moser and Lee in 2015. And there's a database. There's a database right now, I think is at Johns Hopkins, a database for DNS, so direct numerical simulation, fully resolved turbulent channel flow. So then the question is, if you can do DNS, resolve everything, why do silly people, hundreds and thousands of papers, do LES? The reason is what I've described before. Yes, this is a relatively simple test problem. But then you test your model, then you take your model, and then you want to use your LES model, and you want to use it in situations where you don't have a DNS available. Yeah? So it's not like this is a game that we play. Oh, let's try this. It's a very, very well thought out test problem. You use a coarse mesh, so not like this one, but like this one. I'm exaggerating a bit, but yeah. And you require your LES model to give you relatively accurate statistics on this coarse mesh. Yes? And this is not a game. Don't ask me how I know this. Well, I can tell you, but, right? So if your LES model, the LES model that you love most, works here, then you have a chance. It's not an implication, right? It's not math. You have a chance that somebody else is going to use your model. However, if your LES model does not work, so fails for channel flow, the chances of getting it used in commercial software are zero. This is my personal experience. As a graduate student, I was working with LES models, and I still think some of them were beautiful mathematical results, and they had good properties. I really liked them. But then I was told by people in my face, well, have you tried turbulent channel flow? And when I was saying no, they were saying, well, right. This was an issue, and I experienced this myself, right, on my own skin. Okay. All right. Very good. So this is that. Okay. Now, speaking of which, so when I was a postdoc at Argonne, I worked with Paul Fisher. Some of you might have heard of him. It's like he's using spectral element, numerical simulations. And this is one example. So this is the paper we published in 2003, 23 years ago. We had the model. And then what we said is this. Let me see if we can have you see here. I don't think you can see this, but it says Moser and all. This is the DNS database. We used that. We compared our statistics. Right? So these are the Reynolds stresses. Turbulent, under-resolved turbulent channel flow, and we show that we get better results than other LES models. Yeah, and this way, we're hoping that people might use this. So we've seen some people in geosciences use similar ideas. Okay, but nevertheless, I think this is important. You want your model to be used, you have to test it on in LES. You have to test it on an accepted test problem for turbulent flows. Okay, all righty. Okay, so any questions? Any criticism? Not so much more background. Okay, we're gonna get, promise, in 2 hours we're gonna get to what I want to say, the new stuff and crazy stuff. This is not crazy. This is background. Oh, no, it's closed. This is this recorded? Is this oh my gosh, okay. Guys, don't publicize this too much. But anyway, so no, this is the Red Sea overflow. We had an oceanographer working with us, Tamay was good man, and actually, so they had access to ocean data, oceanographic data. Right, so we're looking at the mixing of cold and warm masses of water, and this was too large a problem for us. So then we said, let's look at the Red Sea overflow, which is zoomed, right? We zoom in here, right? And we try to see whether numerical simulations get results that are close, qualitatively close to what the oceanographers got. That was the idea. it has a nice name. So the Red Sea overflow experiment, let's see if it is on the, no. So the acronym for this Red Sea overflow experiment was Red Sox. If you if you like baseball, so I had my collaborator was a Boston Red Sox fan. Was like, oh yeah, this is such a cool experiment. Anyway, right? So that's what we're trying to do, and the way we did it. And I think that this is with this I want to illustrate how LES works for me, right? So this is the oceanographer, Miles Goodman from Miami, University of Miami. Paul Fisher was my postdoc advisor, spectral element guy. So this is what we did. So we looked at the dam break problem. It's also called the lock exchange problem. So you have a box, and then you separate the cold water from the warm water with a very thin wall, and the time t equals 0, you remove it. And then you let the two masses of water like mix. Okay? And what you'd like to do is to capture, right? So there is the Kelvin-Helmholtz instability, right? Because the two fluids, it's not two fluids, but they have, it's the same fluid with different temperatures. They interact, there is friction, and rolls start to appear, mixing takes place. And I even had the movie about, for this. And then they start to mix, and then they settle down to the final stratified, setting. And what we wanted to do is to see if we can simulate numerically this problem for Reynolds numbers and okay, I'm a shorter guy, so it is 1 million. Reynolds number equals 1 million, 3 dimensions. All right, so it was a serious computation. But here's what we did. So this was in Ocean Modeling. That's a good journal in 2009, so 17 years ago. So what we did is we tried a fully resolved simulation, not for 1 million, for 30,000. That's the one in green here. I'm sorry, the last line, 30,000. And we used a lot of mesh points. I want to emphasize that on each brick, we have polynomials of degree 7, 9, 11. So high order, that's spectral elements, so high order polynomial. So really a very fine simulation. This was our benchmark. Then we consider different LES models on a much coarser mesh. Look at this mesh, this one and this one. You can see already quite a bit of difference in terms of resolution. And you can ask, okay, so you use fewer mesh points, how well can you do? Well, if you compare these, they're not at the same time, but if you compare these structures, you can see there's quite a bit of a difference. I mean, you're not gonna see the fine structures from the DNS, but that's to be expected, right? So you have a coarse mesh. The best you can hope is to have some smooth version of this. And I think that if that's what you're looking for, you can get that with an LES model. So to me, this is a good illustration of what LES can do. Use much fewer mesh, so like a much lower resolution. You're not gonna get the same accuracy, but the large features you can actually represent. Yes. They're very small structures. Right. So you're saying that so they have they're like oscillations. That is correct. That is correct. I don't remember like how far we went in the spectrum, but yes. So this was pretty close to a DNS. Yes. But once again, we could afford this because it was Reynolds number equals 30,000. It was not 1 million. For 1 million in 2009, 8, whatever, we tried and we didn't have the resources to do that. Yeah. Yeah, so you can do DNS in practice. I mean, this is also a test problem, but in practice, you can do DNS if the problem is simpler, is relatively simple. But if you want to look at high Reynolds numbers, 3D, complex features, it look, talk to practitioners. Every time I talk with them about LES, they say, oh, I'm an engineer. For me, LES is too expensive. I'm using RAS. That's what they say. They told me in my face. So, I mean, and this is LES, right? I mean, so it's not DNS. Forget about DNS. DNS is, you know, the engineers don't even think about, they say even LES is too expensive. It will become possible soon, but okay. Yeah. It is, that's the practice. There is practical things. Okay. All right. Very good. So that's what we want to do. Now, so, right, I've shown you these papers. So they're models. There's a bunch of models. And I'm going to talk about a special class, a particular class. Now, I was thinking about giving, you know, an intro to POD, to ROMs. And for those of you who have not, everyone has seen it. So I'll go through this very quickly. So for me, the schematic would be this. You start with an equation, a generic equation. You have I think of U as the velocity field, but okay. You take a lot of snapshots, as many as you can, and you do this with a full order model, which means a standard numerical discretization. Myself, I think finite elements. You can use finite volumes, finite differences, what have you. But the important thing is that the dimension, the number of degrees of freedom is very large. It's on the order of millions. That's how I think about it. Billions. Actually, it should be billions. Importantly, I think that's an important aspect. It does not, the snapshots, which are the let's say, velocity field at different times or for different parameters, they don't have to come from numerical results. They can come from experiments. I mean, this is real. People can do that. Yeah. Okay. Then in the second step, the important thing is to get a data-driven ROM basis. So the models that I'm going to be presenting are based on the Galerkin method. And I'm always going to work with a low-dimensional model. So I is on the order of 10. Here I mentioned proper orthogonal decomposition, reduced basis methods, hierarchical basis. I mean, whatever DMD, whatever you want. Yeah. All right. It's important, however, and Thomas came up this morning with a new basis. I'm serious, actually. This is not a joke. I'm laughing, but this is the truth. So we're discussing about, you know, like how to solve a particular problem. And I think, you know, so this, Thomas said a good idea. We have to test, we haven't tested it, but so it is, POD is probably the most popular reduced basis, reduced order basis, but there are many bases, and you know, people develop those even now, I would say. But then, and this is important, one particular class of ROMs is based on a Galerkin method. They don't have to be based on Galerkin methods, as you well know. We believe that the Galerkin method is good for you because you can prove, you know, classical numerical analysis results like stability and convergence and so on. Okay, so then what do you do? So, right, you write your approximation. So you approximate your, let's say, velocity field. You approximate this with your ROM velocity field approximation, which is a sum from j equals 1 to r of time-dependent coefficients times, like in usual Galerkin methods, your basis functions. Okay? You plug this in, project it onto the space, or use a Petrov-Galerkin type of projection. Yeah? And then, at the end of the day, you get a system of equations for, I wrote this in the dynamical systems form, so a dot. I was told that that's what dynamical systems people use. So we have a dynamical systems for a system for the coefficients. That's what you want to find. You find the coefficients, you found the ROM approximation, and you're done. Okay, and I don't. Yes. Yes. True. Okay. Okay. Yes. Yes. And this is good. This is fair. And I did not expect this from you, Birgil. This is actually this is, I was gonna say, you know, tell tell them to contact me and then we'll have a discussion. And no, so okay. So first of all, I want to go on the record. So the idea that POD ROMs can be applied only to elliptic parabolic problems is wrong. It's not true. So it can be applied to any type of PDE, but of course it was better for some than for the other. Now, when you talk about hyperbolic problems, the idea of using POD for hyperbolic problems is still valid. And people use POD for things like compressible Euler equations. Okay, hyperbolic, so there's no viscosity, hyperbolic type of ROM. That's not the issue. The issue that those people, I don't know who those people are, but those people who criticize ROMs, what they refer to, and this is a problem, what they refer to is shocks. You can have compressible flows, slightly compressible flows, without shocks. Like, in fact, like if you fly, right, if you have a model airplane or, right, I mean, so air, so, right, so it don't necessarily to have shocks. Of course, if you go fast, hypersonics, right, if you go fast, shocks are critical. So the whole point is not hyperbolic, it's about sharp features that travel in time. Those are very hard for POD, for ROMs. And the classical example is that you have 1D burgers, so forget about, yeah, but without viscosity. Even with viscosity, it's actually not a problem. And then you have a bump that travels from left to right. That's notoriously hard for POD, because if you want to do POD, what you're gonna get is the Fourier basis, because that's not a localized spatial feature. So when those people, I also had the same, probably the same people criticize me the same question. When they ask about, can you apply your methods? That's what I was trying to say about compressible flows. To compressible flows, my answer is yes, just like Elias. Yes, we can. However, if you really ask about compressible flows with shocks, we have not done that. But people like, for example, well, so there are the people who have done slightly compressible flows, like Farhat from Stanford, Charbel. Charbel has done compressible. That's it. All the Sandia group, they're doing compressible flows, not with shocks. If you have shocks, so there are people like, for example, Matt Czar, I think even Tommaso Tadei. So he was looking at this. You can do that. But Masayano from Toronto, those people, well, Masa maybe less, but Matt Czar definitely. The way they tackle this is the following. Instead of doing classical POD, they look at how the shock moves, and then they have a mapping that reduces the problem, the shock movement problem, to one spatial feature problem. But you see, to do this mapping, that's very costly. So that increases the computational cost of the ROM. So I would say this: if you're interested in hyperbolic problems, compressible flows without shocks, yes, ROMs can do this. It was Colonius and Raleigh, they showed this 22 years ago. So there are ways to do it. However, if you're interested in compressible flows with shocks, I think that's open. Yeah. That's fair. Those people have some, they're correct in that. Is that fair to say, Thomas? I don't know. I mean, that's my understanding. I wouldn't say that it's impossible, but it is open. The problem is this: finding efficient ROMs for compressible flows with shocks. Without shocks, this is done. Okay, that's a good question, and that's very criticism. But those people are mean people. You should hang out with nice people, okay? Not with mean people. No, I'm joking. They have a point. Yeah. What you should ask in return is what method are you using? Yeah. They say like machine learning or something like that. I mean, well, yeah, maybe you can do something like that, but you cannot prove anything about that. So, okay. Anyway, so we stick with the Navier-Stokes, incompressible Navier-Stokes, and the idea is very simple along the lines of what we said. We generate a snapshot, we generate the basis, lower the model, and that's what we're talking about today. This yields a very simple system of the a dynamical system for the coefficients. You have a matrix A, this corresponds to the minus stiffness matrix, and then you have a tensor B that corresponds to the nonlinear interactions. We don't have pressure here. This drops out, excuse me, but that could be added. So we've used different models for that, so that can be done as well. Okay, this is that. Questions, right? So you can use, right? You take that low dimensional model, so you use it either to predict in time, right? So you have snapshots, you train your model, and then you predict longer in time, or even more interesting, I would think, parametric ROMs, in which you change the parameters, like the Reynolds number. This is a little bit tougher. That's what you like to do. It can be done, but it's a little bit tougher because it's hard to go far from the training regime. However, I think that this is general criticism. Even if you use machine learning, if you test your model, if you train your model for, moderate Reynolds numbers, and then you try it for like very high Reynolds numbers, I don't think that's gonna work. Okay, so data-driven models can take you only so far. They're not magic. If you don't see the behavior there, it's hard to predict what you haven't seen. Okay, so this is that. Any questions so far? All right, very good. All right, so here's probably that's the first time that we're gonna see something contentious. And right, so remember when we talked about the turbulent channel flow and the under-resolved regime? Okay, so I want to do the same thing. So I want to illustrate what happens when you do the classical reduced order modeling for, I would say generic standard test problems, right? See what happens. So here I'm showing you 3 test problems. At the top, you have the 2-dimensional flow past the cylinder as the whole at relatively moderate Reynolds numbers. 2-dimensional. The bottom left corner, we have the quasi-geostrophic equations that model the large-scale ocean circulation, also 2-dimensional, but this is chaotic. This is not chaotic. In fact, this is very laminar, and this is chaotic. Now, the third one is the is the turbulent channel flow. And this is a very tough problem for ROMs. And I will explain you why. The explanation is right here. As you know, when you do I'm used to say this for the proper orthogonal decomposition, but the same idea is for any type of basis. So when you do POD, and that's what we're doing here, plotting the decay of the singular values. These are the scale singular values, eigenvalues in the eigenvalue problem. This shows you how much kinetic energy is retained in the first 10, 20, 50, 100, 150 modes. And you can see vastly different behaviors. The best behavior ever is the red curve, which is the 2D flow past the cylinder. It's the best because it says that with only a few modes, you can capture the vast majority of the kinetic energy, which is great. That means that with like 10, 20 modes, you can kill it. You use what I've shown you, the standard Galerity model, you just blow it out of the water. However, another 2-dimensional problem, but chaotic, and you do this, you do the same thing, then in blue, you see the decay of the singular value is much slower decay, which means you have to take many more modes to approximate it. And then the worst from these three cases, the turbulent channel flow with even a slower decay of singular values, which means that for this academic test problem, I mean, not academic, but this basic test problem for turbulence, you would need a relatively large high-dimensional ROM. But you see, you don't want to do this, because if you have a high-dimensional ROM, you may end up spending, as the computational cost could be similar to the form cost. So then why would you do that? Okay. Now, usually what people say is that, but okay, but why do you use, I want to illustrate the need for stabilizations and closures. Because you see, from this picture, I want to use on the maximum, like on the order of 100 modes, 50 modes, but then I see that I don't have enough resolution. And then people ask me, so why do you use closures and stabilizations? I mean, you can just use the model and whatever. Well, you can do that, but if you do that, you're not gonna get what you want. So let me show you what you get for the turbulent channel flow. You can do this for the 2D flow past the cylinder. With 20 modes, you absolutely resolve everything. But if you do the same thing for the turbulent channel flow, you get garbage. So here we have an LES that we use as a benchmark. We build the modes based on the LES. Look at this. R is equal to 100. That's relatively large. Garbage, right? If you tell somebody like a ROMer, I'm gonna use a 100-dimensional ROM, it's like, whoa, okay, right? Look at the you get garbage. So standard methods don't cut it. Okay? And then you can say, yes, Tran, but maybe your Galerkin ROM it has a bug, and maybe it has. Did you write it, Virgia? No. No, I'm kidding. Right? So, in fact, I don't think that it has a bug. I think that this is an intrinsic problem. And here's why. If you look at the kinetic energy, you can see that by increasing the dimension of the ROM, you get closer and closer to the black curve, which is the front. You can say, oh, how about the second order statistics, the root mean square? You can do the same thing, right? So you can go from 50 to 60 to 70, and you're converging. But to get to the purple curve, you have to increase quite a bit. So we get convergence. It's doing what it's supposed to do, but it takes a long time to get there, like a high dimension. So basically, the idea is that there is a need for under-resolved simulations, even if you use ROMs for turbulent flows. People ask me this all the time. I think that this is very important, and I don't think it's well understood, because they say, well, but my model, I have a machine learning model, is working very well for flow past the cylinder, and Reynolds number equals 100. All the models work well for that. I haven't seen one ROM to break down for the 2D flow past the cylinder, Reynolds number equals 1, not one. Everybody is showing this, and then they declare success. But, right? Okay, so now I'm going to show, so we have a problem. I hope that this is clear. We do have a problem, and I want to show you next how we solve that problem. And to do so, I'm going to use filtering, just like in LES. And the first simplest filter is the projection filter. Questions, so other questions about what we discussed so far, the motivation, especially the under-resolved regime and all that. I think that this is, the motivation is important. No, from online? Okay, very good, it's super clear. So the first round filter is the projection. So I want to explain this because people don't usually think about this. This is very similar to the spectral cutoff spectral cutoff filter used in LES. It's the same idea. So you do know that your UR is equal to A1 phi1 plus A2 phi2 plus dot 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 plus AR phi off. And once again, R is on the order of 10. It so happens that phi1 usually represents the large structures, whereas phi10 right here usually represents the smallest structures. It's just like the Fourier, I'm not saying it's the same, but it's similar in spirit to the Fourier setting. So now, so you have a 10-dimensional ROM, right? That uses this approximation. But now I'm doing the following, right? So the 10-dimensional RAM would be this one. A dot is equal to matrix plus A transpose B A, right? I'm using this one. Okay, now, so at any point in time, this is gonna give me an A of T. So let's say A of T, T equals 10, right? And this is giving me an approximation. It's giving an approximation for UR at T equals 10. Right? Now, I can take that, and that is gonna have some large structures like we discussed before, and some small structures, right? Because it involves both these small structures and the large structures. However, if I do the following, if I solve, if I take these coefficients and I say I only keep only 10, the first, so keep only the first 10. The first 5, I'm sorry, coefficients, so half of them. Keep only the first 5 coefficients. In other words, let A6 equals A7 equals A10 equals 0. This is gonna take this signal and it's gonna probably give me something smoother like that. And this is my projection on the 5th dimensional space of my UR. This is it. Yeah. It's a very simple operation. It's trivial. It doesn't involve any effort. And really, actually, we tested this, and this is actually working as a spatial filter. Okay, simple. Another one that is not that simple is the following. So it is 4:30. I know I'm going slowly, but so I think that now we're like catching up. So do you want to take a break in a few minutes, or are you okay? Let me know. What do you think? It's 4:30. So we have 1 more hour. Quarto d'ora? I'm good to go. Should we wait another 15 minutes and then take a break? Yeah? Okay, perfect. So the other filter, RAM spatial filter. This is a RAM spatial filter. So this was the first one was the projection. So this is one. The second one, so projection. The second one is the differential filter. And this is a little bit different. So basically what we do is we start again with a given signal, the same UR, and to compute the filtered solution, we solve this Helmholtz equation, right? So in other words, what we're solving is UR bar minus a parameter delta that I will talk about, right? It's a scalar, yeah? Laplacian of UR bar, excuse me, is equal to the input function UR. This is the same UR that we talked about, right? That's the input function. Because we're solving this elliptic equation, the resulting UR bar is smoother than UR. It has to be smoother. And we saw this in pictures, and I'll show you some at the end, show you some pictures, right? This is a filter. It's a real filter. Now, I think that it also has, so it is not as simple as this one. That's true. And also, I need to explain to you what this is, and I will do that. This is a length scale. It's like the same filter, is the filter radius that's used in LES. It's the same idea. And I also want to point out that this is, you may think, okay, so but then we have to solve an equation. I mean, this is going to be more. What I want to emphasize is that at the linear algebra level, this is equivalent to identity plus delta squared, the stiffness matrix, times the coefficients of the filter function equals to the vector of coefficients. Is the vector of coefficients that you start with. This is an r-dimensional linear system. It is a linear system, but it's very small. It's 10-dimensional. It's not a million dimensional. It's 10-dimensional. You can do this relatively efficiently. Okay. Okay, so this is good. So these are the two filters that I will talk about at first. Okay, so keep in mind this. Yes, yes. Yes, yes.
If you go to the eigenvalue, if you write on the basis of the eigenvectors of that,
That's a good idea. Right, right. So this is a good question. So you are damping, right? So you can see this if you look at the Fourier coefficients. So you are you are damping, right? So it depends on the it depends on the value of delta, but I believe they should. So you're damping all the modes. Yes, yes, correct. That is correct. Right. So yeah, we're not doing. I see. I think I understand what you're saying. So we're not doing preferential type of damping. That's a good question. I am aware of, like, the first thing that comes to mind is, so there have been a long time ago, like Karniadakis was doing, believe it or not, so he was doing spectral vanishing viscosity, where he was, for each mode, he was including a, specific tailored viscosity. The idea was that for the large modes, you need less viscosity, and for the large modes, you need more viscosity. We also do something like this. We have a version of this filter where you use a high order differential operator, like the biharmonic operator, or even so you can tailor a little bit the way you're doing it, but that we do affect all the modes. It is a good point. Yes. Yeah. Okay. So these are the two filters. They're different. They're both filters. They're different, and they have strengths and marks. Okay. Now, this is the first model that I want to talk about. This is so Virgia was part of this. Thomas also. So that's exactly. So we're talking about this this morning, how to improve this. But I want to tell you about the idea of this model. So it's one slide, and I understand that maybe there's a little bit of, it's quite a little bit of material, but here's the idea. So the idea is that, remember when we said that for turbulent flows, classical Galerkin ROMs do not work because they're under-resolved. So the idea here is to supplement to endow these Galerkin ROMs with extra terms that account for this truncation. And these are the closure models. But the closure models that I will present today is a data-driven ROM, right? So let me write down what the idea is. So the idea is that instead of working with this dynamical system, what we're doing in closure modeling is that we add a term that depends on the vector of ROM coefficients, right? So it can be computed, and the idea is that the hope is that this model accounts for the truncated modes. So somehow approximates the effect, not the modes themselves, but the effect of a r plus 1 ... a capital R. So the truncated modes, the coefficients that were not used in the simulation. Of course, it's a very general model, so there are like many, well, not as many as an LES, but many ROM closures. Today, I'm going to show you we've also used many. But today, I'm going to tell you about a closure model that is derived 100% from data. There is no physics, at least as a first approximation. There's no physics involved. Now that I'm thinking, there's no math involved either. It's only data. All right? Okay, so how do we do this? So the way we do this is as follows. I'm not gonna explain maybe all the details, but you can ask me any questions you want about this model. I'm gonna spend time to show you pluses and minuses. Okay, so basically we have the phi r modes. Those are that we keep. And we have many modes. Think of capital R as 1,000 and little r is equal to 10. I keep 10 modes. This is my ROM, my Galerkin ROM. And then I truncate all these coefficients and I replace them with my tau. This tau represents the effect, the interaction between truncated and modes kept in the model. Now, the way we're doing this is a two-step procedure. In the first step, we postulate that our tau has a certain model form that is postulated. So we postulate this. For example, so e.g., tau can be of the form a linear model, or it can be a quadratic model, right? So I'm gonna denote this by a tilde to distinguish it from the Galerkin operator. Or it can be of this form. And you know what? Now that I'm thinking about it, tau can also be a neural network, machine learning type of approach. I'm not going to talk about this. I'm going to talk about the quadratic model. So we postulate this form, and it is right here. And then we solve a least squares problem in which we try to fit the model form to the actual closure term. You see, if we use a variational multi-scale approach, we can precisely write the term that we would need, right, in the r-dimensional ROM formulation, right? So this is the fun part right here in the first line, is the exact closure model. Yes. You mean here? Okay, this is a very good question, and I should have explained this. So we do this for all the components. So this is going to be a vector. So in my notation, I is one of these indices from 1 to r. But you see, so the stress tensor tau. So right, I was a little bit careless here. So tau is actually you see, I'm adding it to this dynamical system. So this is a vector, right? So to define this vector, the way we define this vector is that we compute this, but for each I component. And then we try to match the tau tensor vector, right? Which is right here. This is the model form to the actual closure term, which is also a vector. Correct. That's right. That's right. This is a good question. Yeah, we had a discussion, a long discussion. I remember when we implemented this about what exactly this means, because there was quite a bit. It was not clear. And I think that the reason is this. So the reason is that I tend to work with the PDEs, but then actually, if you look at this is just it's a system of ODEs. We need to be careful here. Okay, so. Right? So the principle, I believe, should be clear. The principle is that you have the closure term exactly. You can write it exactly. I think that that's something different from what many practitioners do. Many practitioners say, I don't know what tau is here. I'm just going to choose some model that gives me the best results. We're not doing that. We're saying we know exactly what it is that's coming from Iliescu theory. We postulate a model form, and then we try to fit the coefficients to find the coefficients that give us the best match. But we're fitting the exact closure model, not, I mean, we know what it is. Of course, you can say, oh, but this is a form, it's a form quantity, so it's very expensive. Correct, but that's why we fit the model form, the ROM model form. Yeah, so this is, when you use this in practice, look at A tilde and B tilde. These are R-dimensional operators. They're very small. Huh? Okay. Yeah, so we feed the model form, we get the best operators, A tilde and B tilde, and then we supplement, we add those corrections to the usual Galerkin operators. This is it. Okay, now we're just chatting that this, to me, this is reminiscent, is I would say that's quite similar, if not the same, as what these quadratic corrections are. So they're like groups in California and Texas, they're supporting this. And actually, in their papers, they do mention that, you know, a similarity to what we've been doing, the quadratic closures. Okay. We published this in 2018, so that's been 8 years. Okay, now, so how does this work? Well, for the turbulent, I'm sorry, 2D flow past the cylinder, it works very well. However, if you want to apply it to more challenging problems, it doesn't, just purely data-driven models, in our case, did not work so well. What worked well are the physical constraints. So look at this. At this point, I said that we find this A tilde and B tilde to match the data. But then we realized that data by itself is not enough. So this is the stuff that we're talking this morning about. We consider the constrained data-driven PMS, in which the constraint is that the tau, the closure model, overall should be dissipative. In other words, if you add these terms, A tilde and B tilde, to your model, the effect of those terms should be to dissipate energy from the system. If they introduce more energy in the system, it's going to blow up, no problem. Yeah. So, all right. Now, the question is this, it's a little bit subtle. What's the difference? You see, this is a matrix and this is a tensor. How exactly do you impose this condition? And the way, and I'm not saying that this is a necessary condition, but it's certainly sufficient. The way we propose this to implement this constraint is by requiring that A tilde be negative definite, and then B tilde be conserving. And you might say, well, Traian, yeah, of course, so this is sufficient, but how did you come up with this? Well, so I want to draw your attention to the original Galerkin model. This is your Galerkin model. If you look at A, this is negative semi-definite, and B is conserving. So if you want to add, if we want to add a B tilde here and an A tilde here, it makes sense to impose the same structure for B tilde and A. I'm not saying it's not a proof, it's not a mathematical proof, but it does work. Yeah. So this is what we used, and I want to show you a simple example, and I know your reaction, you're gonna jump on me, because I'm gonna show exactly the 2D Navier-Stokes. In my defense, is Reynolds number equals 1000, okay? So, and also, I want to draw your attention to the dimension of the model, three-dimensional. With 3 modes, you're not gonna, usually Galerkin ROMs don't do well, yeah? So it's 3 modes. So it's under-resolved. And indeed, if you look at the Galerkin ROM, you're not going to get good answers. But look at this. If I'm using the standard purely data-driven model, look at the kinetic energy. It does well at the beginning, but then it starts to increase a little bit. It doesn't blow up, but you can integrate, it doesn't blow up. But, right, so you can say, oh, but there's not a big difference. That's true. But you see the increase is there. However, if we use the constraints, we actually solve that problem. It's not perfect, but it's a much better approximation. So the physical constraints matter. This is the simplest. We use this for the quasi-geostrophic equations, and there it actually made more of a difference. Yes, Carlos.
Is evaluated on an extrapolation regime or
Right, sorry. Very good. It's a predictive regime.
Okay.
No, this is a good point. Yeah, that's a good point, Carlos. Very good. Yes. So we did look at the extrapolation regime. Okay. All right. So do you want to take a break? Yes. Okay. We'll stop here maybe for like 5 minutes. You want me to pause it or the recording? I mean, I don't care. Okay. Right. So let's leave it. Okay. Very good. So we'll be back at 4:52. Thank you. Some of us. Oh, no. That's
Okay.
perfect.
But can I tell you
Perfect.
something, I think this is the, sorry,
I like it. What's the problem? Perfect.
I think this is okay. I can also do another one.
Thank you, Virgia.
Yeah.
Yes, if you're gonna see this on LinkedIn.
So,
Yes.
I
So,
don't know how long it will take for me. Perhaps I'm finishing by 6, something like that.
Okay.
So
yes, that's
go
okay.
home,
Yes, I understand. I'll see you tomorrow.
see you tomorrow here a little before 9.
Yes, okay.
Okay.
So you want me to, so how do you know? I'll be in my office. Do you want to do, or you want me to come to your office? I can do both.
Tomorrow.
Yeah.
But we can meet here because
Ah,
the talk starts.
I know, I'm sorry.
Is to stay.
I'm
to
sorry.
be here the day
Yes,
before.
yes, I will be here at 9.
I think I didn't
45.
tell you that tomorrow it was at 9.
I think right, because I thought it was at the same time.
No, because I thought you would possibly would like to have some sightseeing.
That would be great. That would be great. Sightseeing, yes.
Sightseeing.
Yes,
Okay, so.
That would be
we
very
have,
nice,
the
yes.
remaining of the day.
perfect, perfect. I will be here at 8:45.
Okay. I'll try.
Thank you. Yes. thank you,
Yes, I can.
Well, no, you don't have to be here, so
No,
I'll.
the point is I usually come by walking, so I'll get the bus. That's it.
Oh,
I don't have even to get earlier. It's just-
really?
No, no,
Yeah, okay,
point is to get the bus.
okay. All right,
So don't.
okay.
Guys, I like.
Yeah,
I
good.
like it.
Yeah, so right now I was slow, but I wanted to make some points because I didn't know the audience.
Yeah.
I thought that there were like gonna be some people who maybe have not seen
Yeah.
ROM and POD. That's why I went slowly. But now it's gonna go faster.
Okay, okay,
Yeah, I have lots of slides, so.
okay.
All right, very good. See you, Thomas. Thank you. It was slow. That was a little bit slow. That would be great. Oh, that would be great. So where do you want to meet at your favorite team stadium or?
No, maybe just the kind of, the various, for the coffee.
That would be great, Virgil.
Maybe something at the.
That would be
workspace.
really good. Very good. Yes,
There?
yes.
Coffee.
Perfect, Virgil. Thank you. So okay, so 8:30, huh? So can we do 8:40 or something like that? 8:40. So yes. No, even WhatsApp. WhatsApp is good. The only thing is that I turned off the data because I'm charged by the day. So I want not to be, I mean, it's $12, so it's not a big deal. But once I get on campus, I have Eduroam. No, I have
Connected with.
Eduroam.
Yeah, and what you can do.
Yeah.
Can I tell you something?
Okay.
For WhatsApp, I can
Yeah.
the.
You're specialist in WhatsApp.
Oh, no, no, for the settings, just allow, you just use WhatsApp without this.
How do you do that? No. So I know that, but I still
that
have,
one, if you go outside.
right. So I still need some Wi-Fi,
Yes. it's
right?
okay.
I understand what you're saying, but it has to connect somehow. So, yes. If you look, I check my email, I get notifications. So every time you send me an email, if I have Wi-Fi, which I will, and
If you go to another place very much.
yeah.
Just fix that place behind you. I just stay and add email, add email, just fine.
Okay, all right. No, but let's do what you said. Let's meet at the coffee. We'll get the coffee. I owe you a coffee, so I buy you a coffee, and then we can come here. And then, like probably in the afternoon, I think if it doesn't rain, I would like to go just walk. The okay. Ooh,
I really like.
let's do that. Yes. Okay.
We can, maybe we can stay until 5, 6.
Okay.
After that, we can.
Perfect.
go, yeah.
If you tell me what, so I don't know what restaurant. I mean, I'm not. I like nice restaurants, but if you tell me let's try this or try that, I would.
Yeah, but I would also suggest for the locals.
Very
For
good.
sure. What I know.
Very good. Okay.
It's fun, but for sure. Especially for
Uh.
you can just explore. I will tell you a couple of places.
Yes.
that,
Yes. Plus, I think Carlos wants us to take us for after the thing, Friday, right? On the list, yeah. Okay. Well, probably. Yeah. Yeah.
I just received, but I didn't know my schedule. This is the reason my school.
I think if you wanna go, then I suppose we will provide another class.
Yeah, but it is just something, yeah, gives you some problem.
And I suppose that it's not that early, like tomorrow I will let you know.
All right.
I'm sorry for the question.
No, that was a very good question. But who's asked? Yeah, that was very good. That was a very good question. Thank you. I realized that. I realized. I know. Okay. I realized that. What's going on? All right. Okay. So we can continue, right? Okay. Very good. So thank you for being here. I understand that this is all right. So I try to go slowly. I have quite a few slides, but I try to go slowly just because I didn't know what the audience was, and I wanted to make sure that everybody's on the same page. But right now, I'm gonna go faster. So you need to stop me whenever it is something that you see something that doesn't make sense. Okay. All right. Very good. So this is this. This was the first test, and once again, I don't think that this is the best illustration of why physical constraints are useful, but it is a very under-resolved case, and it is convection dominated. So you can see that 2D flow past the cylinder, but even in this case, we have an improvement. Okay, now what happens if we go back to what I like, which is geophysical flows? I think that these are very interesting, and I'll show you one example. So this is a quasi-geostrophic flow, and what is interesting, I believe, is the large ocean scale circulation. So here we have gyres. In particular, look at what happens in the North Atlantic. So if you look at the North Atlantic, you can see that you have two gyres, very large structures. Look at this. You have one here, and then you have one here. But not only this, you can see that those structures are not centered in the North Atlantic. These structures are actually squished to the western side of the Atlantic. So there's the boundary layer here, and there's another boundary layer, right? Like right there. This makes it difficult for numerical simulation. You can say maybe that's a fluke, But look at the North Pacific, and you see the same type of qualitative behavior. You have two large structures, and then those structures are squished against the western boundary. The western boundary here is Asia. The western boundary here is the East Coast. And do you know what this is here? Do these gyres seal something like this is the Gulf Stream, right? This is the important current in the ocean that carries masses of warmer waters from the tropics all the way to Europe and so on. So it's an important type of geophysical flow. Okay, now, so what are the equations modeling this flow? And the simplest model for the large-scale ocean circulation are the is given by the quasi-geostrophic equations, the QGE. Here they are. We have two variables, Q, here and here, and psi. The psi denotes the stream function, right? And I want to emphasize that by using the stream function, you can actually recover the velocity, the vector field, right? So if you take minus partial of c partial y, partial of c partial x, you're gonna get the velocity. Now, Q is very much like the vorticity. If you take the two-dimensional Navier-Stokes and you write it in the vorticity stream function formulation, you're gonna get something very similar to this. There's one difference though. If you didn't have this y value, here instead of Q, you would have the usual vorticity. But because of this y value, this is the potential vorticity. And the reason why you have the y here is because you have rotating flow. This is something that you don't necessarily have in the 2D Navier-Stokes. 2D Navier-Stokes without rotations would be exactly this minus this term. This corresponds to the Coriolis force. Because of the Coriolis force, you have this extra term. J is the usual nonlinear term, but now that it's written in terms of stream function and vorticity, you have the Jacobian formulation. And Reynolds number shows up as usual, whereas the Rossby number, which is a measure of rotation, shows up in the definition of the potential vorticity. All right? Okay. And then you're gonna say, okay, so what does this have to do with what we have? Okay, well, here's a test. This is a standard geophysical flow setting. You can think of this as the North Atlantic. Yes, and it's a box, right? So it's a very idealized type of geometrical setting. True, but we have an interesting two-gyre wind forcing. So the forcing term is similar to what people use in geophysical flows. What I'm presenting here is the averaged stream function. So I'm averaging the stream function over a long time period. For the DNS, which is the truth, what you should get is a four-gyre structure. So then the question is, can ROMs of different flavor recover this four-gyre structure? I want to emphasize that this is only an average because the flow itself is chaotic. So you don't have a steady state. Okay, now, if we use the Galerkin ROM with only a few basis functions, so it's under-resolved, 10 basis functions, that's what GROM gives you, completely inaccurate. If we use the data-driven ROM, we get the four-gyre structure, but if we use the constrained, physically constrained data-driven model, we get a significantly more accurate resolution. So in this case, where we have a chaotic flow, the adding physical constraints yields improved results. And actually, there are cases in which if you do not add the physical constraints, the standard model can actually be unstable, right? If you don't, so you get data-driven operators that match perfectly, as optimally the given data. But then that doesn't guarantee that once you take those operators and you put them in the model, the resulting model is going to work well. There's no guarantee, mathematical guarantee. That's correct. That is a good point, but definitely if you look at the testing regime, so you try to look at different parameters in longer times, in those cases you can get very bad results. Yeah, it can blow up because there's no guarantee of stability, for example. It's not a Galerkin model anymore. You have a Galerkin model to which you add a new term. If you don't have some constraints over that term can actually make the model blow up. Yeah. Excuse me. We're using, I mean, we're honest about this. We use the same type of setting. The only difference is that for this one, the constraint one, we do impose the constraints we talked about. That's the only difference. But it does matter. So once again, for the 2D flow past the cylinder was not that important. But in our experience, the harder the problem, the more important these physical constraints become. And I'll show you next. That's a good question. All right. Okay. So this is that. And this makes a point. I think that this makes a point, and the point is that if you use just data, that's one sentence that the take-home message. If you use just data, this data can take you only so far. It does improve the model, and it works well in many settings. But there are situations in which data by itself is not enough. The more challenging the problem, the more important the physical constraints are. Okay, now I'm not going to go through this in detail. I just want to show you an example. So this is Sis from 3 years ago with Omer San's group. We looked at using machine learning. So instead, you see, you can always criticize the fact that, okay, so why this structure? We like structure, because then I'll show you. You can prove something, right? But from a practical point of view, an actual question is, why do you use this structured approaches? And I want to emphasize people doing operator inference, like Karen Wilcox's group, Beherstorfer, or Cindy, like Steve Brunton and Nathan Kutz. I mean, so these are natural choice or symbolic regression. That's quite a. You can use this type of approaches, and they're similar in spirit, adding structure to your data-driven model. But the vast majority of people prefer to use generic neural networks and different types of unstructured type of operators. So that's what we did here, an unstructured type of machine learning. And in fact, we tried to actually not only come up with the closure model for the discarded modes, but even for the idea of projection error, the fact that you do not have enough information in the snapshots. You see, because you go from the continuous level, you go to the POD level in which you take all the snapshots and you squeeze the most out of it, and then you do a further truncation when you use only 10 modes out of like 1,000 modes. So at each level, you make some sort of error. And we can account for part of this error, but not for everything. With machine learning, however, you can hope, because we don't know the structure, we don't have too much idea about how we should model this. But machine learning, since it's so generic, allows you to do that. And you do indeed get an improvement in accuracy in this particular case, right? Yes, so here we have, you see, this is extrapolation in the Reynolds number. It's not a huge extrapolation, but it is extrapolation in the Reynolds number. Right, so this is in sample from 500 to 1,000, and out of sample is from 1,000 to 3,000. And those that work better were not, so these are VMS, data-driven VMS. These are standard machine learning. And these two, orange and purple, the best, are using an extra layer of machine learning for the layer that goes from the continuous model to the space of snapshots. Right? Yes. Yeah. All right. Okay, that's a good question. Okay. Correct. Yes. You're right. Yes. Yes. You're correct. So this is something I did not talk about. So I just presented this as the basic vanilla flavor in which we look at the interaction between, you see here, I just showed you the interaction between the modes that we keep and the modes we discard. But you can think of it in a different way. You can think as a 3-scale model in which not only do you come up with the model for this interaction, that's what we've done already, that's a 2-scale one, but you can come up with the model for what happens when you go from this to this. So this would be 3-scale and this would be 2-scale. Just like in VMS, you can play this game of like taking more and more beams for the scales. And yes, as you correctly noticed, you do get an improvement in accuracy. It's a little bit more work, but I think that it does. It's a more physical model, because what happens between large scales and small scales, the better it's like in a sense the spectral vanishing viscosity that I talked about. You have to do different things, ideally, different things for different modes. Ideally, that's what you'd like to do. The more you do this, the more accurate, but also more complex. And yeah. So, but that's correct. The 3-scale model is indeed more accurate. Okay. Now we just to show you. So I think that this is interesting. This is the full order model. And then if you take the full order model, project it onto 6 modes, that's the best you can do. If you project it on 20 modes, you get a better result. However, our model is using 6 modes, is doing better than the projection, which is crazy. How can you do better than projection? But the whole idea is that we have a cheap machine learning model for the interaction between the modes that you didn't use. Yeah. Okay. This is this is another thing that I think should be. I learned this a while ago so it's used in engineering. These are Pareto plots. I think that these are important. So in Pareto plots, what you do is that you have one axis that represents the error, and then you have another axis that represents the time. And the question is, of course, we usually show this axis. Which model gives you the best error? But I think that this is a little bit more delicate. So you also have to look at the computational cost, because if you decrease the error by 10%, but you spend twice as much time, then you shouldn't use it. But look at this. So if we plot the different models, different flavors of models, and in our investigation, the nonlinear POD models. So when you plot these data points, what you would like to do is it's like the L curve. So if you take any book on image processing, you look at the regularization, right? You look at regularization. So you would like to be you'd like to be as close as possible to this corner. The closer you are, the better you are. And in this case, the physics-guided machine learning part does give the best results. Okay, so this is a good idea. Right. Very quickly, we really spent time. Our groups, just a second. Yes, sorry, give me 1 second. So our group spent a lot of time on this model. It's one of our favorite models. Virgil, is that correct? Absolutely. So Virgil was part of the development, right? So, and we went in different directions. We looked at the pressure. This is something that comes from CISA, from the CISA group. Was not our idea. It's a very good idea. So this is not LES. LES people don't do pressure closure. Because what do you do? You just come up with eddy viscosity pressure, I mean, right? But if you use data, you can actually come up with improvements. And this is a nice idea. We use machine learning. This is symbolic regression of a recent paper. And we also have a stochastic version, and I think that that's important. I think that's the future, honestly. We're deterministic people, but I think if you look around, I think this idea of stochastic, a stochastic formulation is closer to the idea of turbulence. I believe in statistics for turbulence. I don't believe in pointwise errors. Those are hard to get for turbulence. And numerical analysis. And finally, well, Thomas left, but with Thomas's group here, we looked at the residual. This was the Seville idea. We looked at using residual formulation. I didn't show you. I didn't talk about this, but I think that's a good idea. Okay, so that is that. If you want, I can talk about any of that. And then the next thing is let me see. I've talked so far, I've said only why this model is a good model. And the next slides, in this slide, I want to show you that there are many issues, okay? So some bad news, some bad stuff. I want to say bad stuff about our favorite model. Sorry, Virgia, ask me the question. You wanted to ask the question. Okay, yeah. Yes.
Because I think you are just comparing the offline competition.
Okay. Okay. Yes. Probably so. Yes. Yeah. Right. Well, wait. So the GROM, the 6-dimensional GROM is no, right. So the 6-dimensional GROM, in terms of error, is the least accurate. So this makes sense. However, in terms of computational cost, is very cheap.
I mean that what we are.
I don't remember. Right. So yeah, I have to get back to it. Yes, I don't know. Yes, I don't know. So that could be the case. I'll get back to you on this. I have to look at the paper. I don't remember off the top of my head. No, but I mean, so yeah, yeah, I'll get back to you on this. That's a good question. Okay, so far, once again, only good news. We really like this model. We spent time on this. I think it's a good model. Once again, bigger shots, bigger groups nowadays have similar ideas, right? Quadratic corrections, yeah, very similar to what we've done. So must be a good idea, right? The big shots use similar ideas. That's a good thing. However, there are issues with this. And this is an important slide, in my opinion, although it has negative news. So we tried it numerically for the quasi-ideal structure, for chaotic flows. Definitely 2D flow past the cylinder, convection dominated, unresolved, worked well. When you went to the turbulent channel flow, we had issues. And I would say this. I would say that to summarize this slide, if you look at second-order statistics with the turbulent channel flow, so the Reynolds stresses and the RMS values, not the average, not first-order statistics, those would get well. We approximate those accurately. But the second-order statistics, to summarize, the take-home message is that our favorite model, by itself, data-driven, with physical corrections, fine, by itself does not work. What worked for us, just like in LES, was a hybrid model in which our data-driven model was supplemented with a little bit of eddy viscosity. That's what worked best. And I want to emphasize that we tried to turn off the eddy viscosity, obviously, that didn't work, so the original model, data-driven model. But you also tried to turn off the data-driven model, just eddy viscosity. That didn't work as well either. What worked well, just like in LES, was a combination of math, data-driven, with physical modeling. And this is a red flag. This pretty much, in my opinion, this is a personal opinion, I think that that might be, you know, more of a general statement. I believe that using physical models in conjunction with data-driven models is the way to go when you do turbulence. I don't believe that magical black box off-the-shelf machine learning data-driven models will do everything in turbulence. I don't think those are gonna work. And I haven't seen too much of that. Okay, so this is the strong statement, and it's a conjecture, and we recorded, hopefully. But what I said about LES is true. We were part of the group when I was a graduate student that was doing a priori testing. We're fitting perfectly offline closure models. But then engineers were criticizing us that, okay, but when you take those models that perfectly fit the closure model and use them in a posteriori testing, which is you plug your model into an actual LES model, we're getting oscillations. And they were saying, well, if we use the data-driven Smagorinsky model, we get better solutions. And that the data-driven Smagorinsky model was not matching the closure model, but it was working well in practice. And the whole idea was that that was dissipating energy at the right rate and so on and so forth. So you see, those guys decades ago had similar experiences. They were trying to offline to train their model, but then it was not working well in practice. And the best solution was actually using those good a priori models with a little bit of eddy viscosity. Like, for example, approximate deconvolution plus a little bit of eddy viscosity. Something to remember, you don't see it. If you do 2D flow past a cylinder, a Reynolds number equals 100, this doesn't matter. Data-driven modeling is gonna give you best results. But the second you move to turbulent flows, under-resolved turbulent flows, you will see this kind of stuff. Okay, so that's that. Okay, now this is you know, I'm sorry Thomas is not here. This is one of the strongest numerical analysis groups for LES and ROMs. So it gives me great pleasure to show that our data-driven model has mathematical support. All right. So what we're showing here is right. So Virgia was an author of, on this paper. This is work with Gianluigi Rozza and Chang Hong, my colleague Hong Hu, and my former student, Zhuang. He's a professor now, University of South Carolina. All right, so this is called verifiability. And the idea is very simple. I'm not going to talk about, you know, in this setting, I can talk about the details. But basically what we're proving is this. If you can guarantee that your ROM closure is accurate, is close to the form closure, exact form closure term, does this imply that the ROM solution is also an accurate approximation? And we prove that this is the case. Prove that this is the case. And I want to emphasize that the closure model that we're using here is purely data-driven. So we use data to construct it. We don't use a Smagorinsky ansatz, or so we did that too. But for this particular case, we use the data-driven model with physical constraints. So those physical constraints are used in the definition. But then for this data-driven closure model, we can prove, you know, this verifiability, a natural result. And I'm wondering how many data-driven models can claim the same statement. If offline training is accurate, can you guarantee that the resulting solution is also accurate? prove. So I think that this is nice, that this is one advantage of doing data-driven modeling, but in a Galerkin framework. If you don't do it in a Galerkin framework, I don't know how to prove it. Okay, so here comes a pop quiz. It is, we're like 5 minutes away or so, 7 minutes away from the, right? From the, is this, so we have 7 more minutes, right? Or not?
Yeah.
Okay, very good. Very good. I have a pop quiz. Okay, this is a serious, so this is very shallow, this is very silly, but I want to see if you can come up with the right answer. Yeah, there's no, okay. I'm just making a point here. So we have a model, you can vouch, can confirm this. We really like this model. We worked hard on this model. Accuracy, check. It is accurate. Efficiency, check. Mathematical support, check. Data-driven, everybody likes data-driven, check. However, I claim, I know, that it's not gonna be a solution if you want to implement it in commercial software. And my question for you is why? For a mathematician like me, this is like mind-blowing. It's accurate, efficient, so it works well, and you have mathematical support. So why wouldn't people implement this model? What do you think? It's very silly. Don't think deep. Don't think about like Sobolev spaces or, think about practitioners. So why wouldn't practitioners use this? Come on. You need data. Okay. You know what? I would love if people thought like you. But they say, oh, so what? We get all the data we have and we plug in and see what we're gonna get. I mean, that's a serious concern. But I would say that this is a serious concern for all data-driven models. If you don't have enough data, it's very hard to get good model. But it's a good point. But no, it's more good try. That was a good try. No, that was good. That would be extra credit. But it is much sillier than that. Much less scientific than that. It's a practical reason. The reason why people are not gonna use this is very silly. And I was told in my face, it's because it's not easy to implement. So it's very silly, but it's true. So I have collaborators at national labs, and I always talk with them and I say, look, we have good models. I mean, they have everything. They say, Traian, who's gonna do this? Right? I mean, you have to have good people. You cannot just choose so that they know what the code does to get their hands dirty, to like closure model, to look at the weak formulation. Who does this? You talk with engineers. I collaborate with engineers. I'm married to an engineer, but okay. So, you talk with them and say, hey, can you use this model? They say, no, I'm using Abacus. When you use Abacus, they don't let you access the code, right? And you pay big bucks for that, right? But they don't, it's like proprietary, right? So you need to think about these practical aspects. Yes, these are beautiful models. They do this and they do that. But when you talk to practitioners, engineers and people at national labs, they tell you in your face, we cannot do that. Right? Well, right. So sometimes they don't have the equations, but I will tell you this. This is the usual statement, but actually like what Karen Wilcox was saying like 10 years ago, it's much shallower than that. Even if they have the equations, they say, bro, we have hundreds of thousands of lines, millions of lines of codes. People spent 10 years, they left. They're not here anymore. Who's gonna go there? Like say, check, we have input and output and that's it. So even if they have the equations, they know what they have to do, they know what the code does, they don't want to get into that. They say, we cannot afford this, right? So you have to do something, in my opinion. Remember when I said I want this to be implemented, you have to do something that people, like not normal people, not good students and good people. So normal people that work in a normal an engineer, regular engineer, right? Those people can actually do it. If they cannot do it, the ugly truth is this one. It's very, as a mathematician, as a scientist, I was shocked and upset. But that's the truth. Huh? Yeah, yeah, correct. Yes, that's correct. Right, right. Yes, yes, correct. Yes. Okay, so I will tell you what. In fact, remember, so I wrote here, I said you can use A tilde, B tilde, or you can, right, machine learning. And that's what we've done as well. We can do this. The problem with this is that it doesn't satisfy what one of the requirements at the beginning. So yes, you can implement it in commercial software, and yes, you can get decent results, as you said. But one thing that you cannot do, I will say it, is to actually prove something. You see, we prove something. I want to know, for example, if you give me more data, do I get a better, more accurate solution? How do you know that? In fact, if you change one regularization parameter in the machine learning, you can get a completely awful results. And the parameter goes from 1 to 10 to the 7th. Like this is an actual case. I didn't know about this. I looked at the code. I was told that like the parameter goes like it's 7 orders of magnitude. Yeah. When you ask, so what does it mean? Oh, well, we don't know. It doesn't have a physical meaning. Right? So then you say, oh, the parameter should be 2.3 times 10 to the, how did you find? Well, trial and error. So if you change that, oh, we don't know about that. So you see, I want to have some sort, I'm not saying Sobolev spaces, I get that. But at least if you double the amount of data, do you get a better solution? That's a simple, even more even shallower. Is your ROM stable? Can you prove that? No, because you change the parameter, it blows up. Well, right? So yes, you can do machine learning, and that's what people like at the national labs. However, customers, when they say, oh, but I want some guarantees, that's when the problems start. If you don't want guarantees, if you just want some results that make sense most of the time, I agree with you. I don't think we can beat machine learning. I think that's the future, then you should focus on that. I agree. But if you want some mathematical support, like solid, yeah, I don't think that's the solution. Okay, maybe we stop here and then continue tomorrow at 9 o'clock. Everyone, thank you. All right. All right. Thank you, Carlos. I appreciate it.